Okay. So we are going to start now decision trees, which are the very basic. Basically, decision tree is the most basic model on which there are other models like random forest, bagging, boosting. These models are built over this decision tree. So first you need to understand decision tree, and then we will see how random forest and all works. So let us start with decision trees. Basically, I will show you how decision tree look like. Then we will talk about decision tree. See, a typical decision tree look like this. Can you see this?
No, I haven't see your screen.
Okay, so yeah, I will share my screen. Can you see it now?
Yes, yeah.
Okay. So we are going to start with this decision trees, and we will be seeing how a decision tree looks like and how it does the classification. Okay. So in a decision trees, basically first you remember what is your data. Whenever we talk about
Okay,
logistic regression, linear regression, whatever, KNN, we have a data, we have a training set where we have number of records, right? Say
mm,
data points, say 100 samples or say 500 samples, and their attributes. So basically those are called features. So we have data and we have features, right? And so if I give you an example of this data and features, so you can simply see the iris data set, right, which we talk about mostly. In iris data set, say suppose you have 96 samples into 4. Now what is this for? Sepal length, sepal width, petal length, and petal width. So these are what? These are basically features. These are features. And the value, the samples, these are called data points, right? So so this is basically a typical data set which how it looks like. Basically, we will have n number of rows and m number of features. This is basically number of features, and this is number of samples. Number of samples. So this kind of data you have. Okay. Now in a decision tree, what happens? Basically what you will be doing is, see, like this is a training set, this one which you can see there are three attribute and the class is given yes no like this. Okay. Now through this data you will be learning a model, and on that model you can do testing. How come testing? You give the three attributes and it will tell you which class it is, whether it is yes or no. This is a very generic example. I will tell you a specific example like this. Okay. In here, if you see the training data, you have three features. One is refund, yes, no, no, yes, no, no, yes, like this. Another is marital status, single, married, divorce, something like that. Then taxable income, and then cheat. Cheat is like the class, no, no, yes, yes. So basically, you can consider this as a problem of whether you are going, if you are going to a bank for loan, so the loan people will be checking for these three attributes. This is just an example. They will the bank will check these three attributes and they will decide that whether you will be cheating them or not. What do I mean by cheating them? Whether you will be able to pay back your loan or not, or you will just default it. So and depending upon whether the software says yes or no, the bank then decides whether to give loan, to pass the loan or not. So in this case, if you see the row number 5, if your refund status is no and your marital status is divorced and your taxable income is less than say 100k, then there may be the case of cheat. So you may cheat in these cases, or whatever. There are three yes cases. So this is just an example. Now a typical decision tree, how it looks like, is drawn on the right side. Decision tree is nothing but a tree with lot of ifs and buts. Like there are ifs, lot of ifs basically. So just like there are three features. So on these features you are going to decide whether yes or no. So how are you going to decide? Basically those are your non-leaf nodes. In decision tree, you see this is your root node. Then this is your, these are your leaf nodes. Why leaf? Because they are not extending to another node. These are the end nodes. And the yellow ones are basically your features, attribute, which are non-leaf nodes. So how a decision tree is made? Like suppose refund. We suppose we start with refund. So if refund is yes, then the cheating is no. I mean there is no cheating. If refund is yes, then always the person will not cheat. No. If refund is no, then you cannot say. So then you will again check another feature, marital status. Again, in marital status, if they are married, then you will never cheat. This has been made depending upon this table only. If marital status is single or divorced, then we will check for tax. If the tax is greater than 80k, then it is yes. If the tax is less than 80k, then it is no. I mean, depending upon this table, they have made something like this. So basically, on the basis of attributes, you split your data. How it is, if you look at the model, what it is doing actually, whatever data is coming, it is splitting it either on the right side or the left side, and then coming to a conclusion whether the guy will cheat or not. So the conclusion you will always get at the leaf node. Whenever you will reach the leaf node, you will get the conclusion. Okay. But you may say that why to start with refund? Why not from why not we can start with marital status itself? So yes, there can be another decision tree, another example of decision tree. There could be more than one tree that fits the same data. Okay, so this is another tree from the same table where the marital status is considered before. So initially we are considering marital status as the attribute, and if the guy is married, we say that he or she will not cheat. If the guy is single or divorced, then we will go for refund. And further, if you are not able to decide with refund also, because refund is no, then you go for your tax income, and then you finally decide whether he is going to cheat or not. So basically from one data set you can make numerous decision trees depending upon what attributes you have basically. So here if there are three attributes, you can make three decision trees, right? Or maybe more, maybe three factorial. Okay. So these many decision trees can be made, but one very genuine problem which maybe you might be thinking, that how to decide on that. Okay, you said you can have n factorial number of trees. If there are three features, you can have maybe five, five or six kind of trees. But then the question here is, how do you decide? You cannot go on doing all that, and which decision tree to choose. Say suppose I told you that this is also a decision tree and this is also a decision tree from this for the same data. So which decision tree to use? Like you can have 100 of decision trees if you have more features and more data samples maybe. So how do you decide on which decision tree, or rather, I would rephrase it. How do you decide that on which attribute, on which feature? How do you decide on that, on which feature, on this feature I will be, on this feature I will be splitting first, and then I will choose this feature, and then I will choose this feature. How do you decide that? So for that kind of decision, of course, you need to decide that, and that is why decision tree algorithm is used. So the decision tree is a machine learning model which uses some algorithm to basically split the data. Okay. I will give you a example. So yeah, so this is again the same pipeline. You train your model. Once your model is trained, you can apply your testing data. So suppose before going to the algorithms, which tells on which feature to decide the splitting, we will see how decision tree classifies the test data. How do you classify the test data in the decision tree? It's very easy. How does it work actually? So see, suppose you have this test data where refund is no, this one I am talking about. So suppose you have a test data where refund is no, marital status is married, income tax is 80k, and you have to find this cheat whether it will be yes or no. This you have to find, okay? So anyway, just see how it will go. So you start from, say, this is your decision tree. You start from root of the tree. Okay. So first refund. So refund is what? In test data, refund is no. So then it will come to marital status. Marital status, what is marital status? Married. So it will come to no. Assign cheat to no. It will not go on checking taxable income. Why? Because with refund no and marital status married, it came to the conclusion that this is not going to be cheat. Okay. So like this, basically you can go through the decision tree top to down and come to a conclusion that whether which class is it, or whether it is going to be yes or no or whatever. Okay. So this is a very easy thing with decision tree to decide on some test data. But the problem here is not the problem, but the beauty of the model is to learn this tree. Once the tree is learned, it's nothing to just go down from top to bottom, you know, uh, coming to a conclusion that which class it is. Okay, that is why I told you, this is also a classification problem, a supervised classification. So that you can
Hmm.
easily do once the decision tree is learned. But the learning of the tree itself is an algorithm. It learns through an algorithm, and it's very important to understand that. Although you have libraries which will do it for you, so but you should have that feeling or intuition of the decision tree, that how it is built actually. So we will see this. So yeah. So basically, if you see the decision tree, there are three commonly used measures, or so you can algorithmic types through which decision tree can be learned. Okay, one is entropy, another is a Gini index, and third is classification error. These three measures are, you can say, used to learn the decision tree, in which Gini index is most widely used and most popular. Scikit-learn and all, which we use library, that library also uses the Gini index only as a default parameter. So that's what that's what we will do. What I will be covering is, I will be covering this Gini index only, because it is very popular and it is most commonly used. Of course, entropy and classification error can also be used, but we will be going by Gini index only. We will be seeing how Gini index is calculated and how the tree is learned. First of all, here you have to understand that the purpose of these measures or of these algorithms is to learn the decision tree. First, you keep this in your mind that why are we studying this? So that we can learn the decision tree. We can make that decision tree automatically through program. Okay. So in that Gini index is used. Now I will tell you.
So,
Yeah.
is this decision tree is a linear or non-linear algorithm?
Linear or non-linear algorithm, I don't know what you are trying to say with linear or non-linear, but the testing is in log n times. So, in fact, if you ask me the complexity of the model while testing, it is even better than linear.
Okay.
It is log of the linearity basically. It's log n. I mean, I will tell you. It's log n. Okay. So why and where n is basically a number of features,
Number of features.
number of basically depth.
Mhm.
So why I am telling you is this: when you make the decision tree, you will be doing like this, right? Yes, no, yes, no.
So there is a relation between features.
Yeah.
Is it right?
So
Yeah.
these are features only, na.
Yes. Yes.
So whatever, see what I am trying to say. Whenever you come up with a test data, test vector, suppose this vector will
Mhm.
go through this tree. So whatever be the is the depth, say
Mhm.
this is not depth actually, I will tell you. So suppose you have this kind of tree. So any test data you take, how much time it will have, what will be the complexity? See, any test data you come, it will try this, either go this side or this side, then try this, then come to the leaf node. So two. Just in two times,
Yes.
it will come down to the conclusion that which class is it is. So
Mhm.
that's what I'm saying. The
Yes.
complexity is the depth of tree. Now, how that tree is built, that is another thing. The tree may be built by log n, where n is number of features, or not number of features. Yeah, maybe the number of features. So, but the point is that it will take very less time in testing. So, uh, it's even better than linearity. That's what I will say. Although the
Yes. Yes.
training
Okay.
will not be linear, training will be a little more, the complexity will be high for training. I am coming to
Oh,
that only, Gini index basically. Okay.
okay. Okay.
So, yeah. So this is how the Gini index is calculated. So what I am trying to say here is just try to understand. Suppose you have 45 data points. How many data points? 45 data points. At the root node, you have 45 data points. Now, and you have three classes A, B, and C. Now, just take an example. When you split this tree on based on some attribute you splitted it, and this one got 45, this one got 0, and this one got 0. This is A, this is B, this is C. So here, basically, all with this attribute, all the data points, all the data samples were detected as A. So this is the best splitting. This is best splitting. Why? Because you are totally coming down to conclusion that what is the class of these data points. Okay, that's what I am saying. Like, how do you split on this node? Suppose you are splitting it on sepal length. Suppose you are splitting it on iris dataset sepal length. So you split like this. If sepal length is greater than 5, then go this side, otherwise go this side, like this.
Yes.
Okay. Now, this threshold is decided again by the algorithm itself. What basically I'm trying to say here is, just try to understand. Here the samples were 45, which got splitted into 4500. So that means it's a very pure splitting. Out of 45 data sample, I have no confusion, and I directly know that all the data points are of A category. Now in this case, this is first case, this is second case, this is third case. Let's say take the second case. Your samples were 90, you have 90 data points. Now when you splitted it on some attribute, again you split it like this, and like this, 3 times. Then on this node, you got 0, on this node you got 45, and this node you got 45, and this was 90. So now this is a bad splitting. Why? Because this split cannot recognize which class you are. It is confused. It is confused between 1 and 2. It is confused between these two. See, this is class A, this is class B, this is class C. This is class A, this is class B, this is class C. This is A, B, C. Now this guy is confused here whether I am B or C even after the splitting. So we will see how this Gini index is calculated. And in the third case where you have 135 samples, 45 into 3, and when you do the splitting, all these 35 samples are equally divided upon A, B and C, which is very wrong. Which is like there is no advantage of splitting, because your data points are equally divided into class A, class B and class C. So there is, I cannot conclude, I cannot come to a conclusion very well on these samples basically. Now first of all, we will look how this Gini index is calculated. So the formula for Gini index is this: 1 minus summation, basically probability, J square. So I will tell you, you see samples are 45 and values are this. So how it is calculated? 1 minus sum of. Now what is the probability that all the 45 values, all the 45 samples basically are of class A only? So what is the probability? The probability is 1. 45 out of 45. And for this B, 0 out of 45, for C, 0 out of 45. So when you do 45 by 45, it will become 1. And this will become 0 and this will become 0. So 1 minus 1. This one minus this one will be 0. So just remember, when Gini is 0, it means the node is pure. When Gini is 0, it means the node is pure. And what do I mean by pure node? Pure node means this is going to be the best split and you should go ahead with this kind of split. I mean, on whatever feature it has splitted very well. Okay. Now in this case, if you see, the Gini is the number of samples was 90, and the value in which they got a split is 0, 45, 45. Here when you calculate this, see 0 out of 90, then 45 out of 90, and then final 45 out of 90. So this is like, and you square also, basically you have to do the squaring also. So 1 by 2 square, it will become 1 by 4. Then again 1 by 2 square, it will become 1 by 4. So this 1 by 4 plus 1 by 4 will become 0.5. So this is basically an impure node. 1 minus 0.5. This is a impure node, and the splitting is not recommended. Why not recommended? Because your data points are splitted equally. Okay.
Okay.
Now in this case, where your number of samples have again increased to, I mean, is the third case where we have taken number of samples equal to 135, and still the values are equally divided. If you calculate the probability like this, it will come out to be this 2 by 3, 0.667. I am telling the our objective is to get this zero, no, zero purity. Gini index, the lower the Gini index, the better the decision tree. The better is the decision. You know how I am telling you, may be confused that what is this 45, 90, 135. So what I will do, I will give you a proper, example. I will give you a proper example. See, just suppose we are getting this a problem where you have say 100 samples. How many samples?
100.
100 samples. Now out of this, see, these 100 samples are there, and this is the first, say, uh, first attribute. Say the attribute is, say, uh, gender. So if it is a male, you go this side. If it is a female, you go this side. Now when you split it, you will find that when I split on the basis of gender, I got, say, uh, I got, say, 100 samples were there, na? So suppose you get 40, 10. Class A 40 and class B 10.
Okay.
And then in here you got, say, 30, 20. Again A, B. See, if you add all of them, they will sum up to 100 only, right? 40, 20, 40, 10 and 30, 20. Now you tell me whose Gini index is better, this one or this one? Whether this is a good split or not.
First,
So
first one.
yes, this one is a good split, because when you are splitting on this side, if you calculate the Gini index, the Gini index will come high. It will come a high value. Why I am telling this? Because this is something where you can at least decide that, okay, the A class is more probable here. 50 out of 50, 40 times A is there. Here it is something like homogeneous. For both class, same number of data points are getting divided, isn't it?
Okay.
For both class, same number of that is decided, right? So this is again, this one is the right thing to do. So on the similar ground, we will see an example maybe. Okay. So this is, you understand how this Gini index is getting calculated
Yeah.
for a particular node. At least for a particular node, you might be you may calculate the Gini index, right? Now,
Yes.
yeah. Now the question is, which on which attribute we should split, whether on which attribute we should split, whether we should split it with first feature or second feature or third feature. Like, how does decision tree decide to take the first feature? So that is actually decided by this Gini index only, but a more better measure called as information gain. Through information gain, we actually decide how a decision tree is going to learn. And what do I mean by this is, through basically information gain, we decide that on which feature we should split initially. Okay, because then you will be confused at which feature to choose. So for that, information gain is used. The formula for information gain is this, where the just don't be afraid by the, I mean, just don't be confused by these terminologies. These are very easy. This is basically nothing but Gini index of the parent node. Suppose this is how you are going to split. Okay, so this is Gini index of this node, parent node. This is Gini index of ID left node, and this is Gini index of right node. Okay, and this is nothing but the normalization term. Why normalization term? Because you have some number of samples, right? And when you split those samples into left and right, you may get a different. It will not be splitted equally, right? It may get decisive, and so for basically normalizing these factors, we have this number of samples which went to left divided by total number of samples which went right divided by total number of samples. When you calculate this information gain, you calculate it for all the features, whether it is refund or income tax or marital status, whatever feature you have. You calculate this information gain for all the features and just see which feature has the highest information gain. And that the feature with the highest information gain will be the first feature on which the splitting will be done. The feature, the attribute with the highest information gain will be the attribute on which the splitting will start. So let us
Okay.
take an example of this information gain, because if you just stick to the theory, it will become little confusing. So what I will do, I will start a, we will see a typical example. Can you see this slide? There are two features, A and B. How many features are there? Two features, A and B.
Two.
Now the question is whether we should split with A or we should go with B. You just see A. There were when you had the samples, initially we had 80 samples. How many samples we had?
80.
80 samples. In this 80 sample, I have say 40 cat and 40 dog. 40 cat and 40 dog. Equal balanced classes I have taken. 40 images of cat and 40 images of dog. This is what I have taken. Okay. Now, when you split it on A is some feature. Say the maybe the cat, the some feature, the
Color,
age of, yeah, the color or something,
color.
some feature, right? Now, when you
Hmm.
split on this, you found that the left hand side gives 30 10 now. Means say 30 of dog and 10 of cat. So if you are coming on this node, most probably you are going to get a dog. Similarly, on this side, you got more cats and just 10 dogs. Now, whether you should split on A or you should split on B, where if you see this, here again 40 dog and 40 cat, on right when you go, on some feature B, on some attribute B, on right when you go, you get 20 and 0, 20 dog. I mean, if you are coming to this node, you are definite that it is going to be dog. If you will see the Gini index of this particular node,
Hmm.
it will be 0. Pure node. It's a
Hmm.
pure node. So, and this rest of the 60 images, it when you go on right, it categorizes them as 20 dog and 40 cat. So again, may not be a good scenario, but so whether we should go by B or we should go by A in splitting.
B.
Yeah. So if you, so that's what. How do you say that B? Okay, you said B because maybe you saw that okay, this 20 0 is perfect and 20 40 is still fine. Okay, good to go. And here you saw 30 10 and 10 30, so you said no, no, maybe B will be the answer. But accurately, if you have to, if the computer has to decide accurately what it will do, so it will calculate the information gain of these two features. What will it do? We will calculate the information gain of A and B, and you will find that the information gain of B is better than A, as it looks like also. B is better. Okay.
Okay.
Now, just go. We will go to the, yeah, the information gain. So this is information gain with Gini index. Okay. Now, if you see this, this is just a very simple mathematics, I will tell you. You remember, on this example only this mathematics has been done, okay? So you
Okay.
just remember this example of A and B splitting. You see, this is my formula, this was my formula for information gain, isn't it?
Yes.
And this is my formula for Gini. So what I will do, I am first taking A, first taking A, and then maybe I will take B. So you just
Okay.
see A, the splitting of A. What is the Gini index of parent node? 1 minus. In parent node, all the data samples are balanced 40-40. So 40 by 80 plus 40 by 80, that will come out to be something like this. Okay.
Okay.
Now, what is the Gini index of left hand side node? This one.
Yes.
30 10 and 10 30. See, left hand side will become something like this, 30 by 40 and 10 by 40,
Yes.
isn't it?
Yes.
And so it will come out to be this. Again, on the
Hmm.
right, what it will become? 10 by 40
10 by
and
40,
30 by 40,
30 by,
isn't it?
yes.
Like this. See, 30 by 30 10 and 10 30. So both has to be 30 10 and 10 30. Just the formula I am keeping. What is the Gini index of the parent, then left, and then right? Okay, and then fit these things into this formula of information gain. So what it is saying, information gain of parent 0.5, this one, minus the information gain of left and right. Basically what I am doing, I am subtracting the Gini index, or you can say I am subtracting uh, the children from the parent, and to
Okay,
come up with a value that I can decide on, that whether it is good for a split or not. So this was parent, this was the child, and this was the another child. Left, right. Okay. Now,
okay,
if you calculate this, it will come out to be this much. Now again I am saying for B also you calculate the same thing. When I am saying B, what does that mean? This one. For this one also you calculate the same, and you will find that B also, the parent will be same, right? 0.5,
okay,
because it's 40 40, and the left is now this 20 by 60 and 40 by 60, which is 0.44. It's a bad Gini index. But you see the right side, 20 by 20 full and then 0. So it will become 1 minus 1, 0. This is a pure Gini index, best case. Okay. And now when you calculate the overall information gain of B, you will find that 0.5 minus this one and minus 0, the pure mode. So when you
okay,
subtract this, it will come out to be 0.17, and it was 0.12. So which one is greater? This one. So the Gini index favors the split with B attribute, B feature. Okay?
okay,
Because
okay,
for whichever feature A or B, the this thing will come high, information gain.
okay,
That feature will be selected basically. Okay?
okay,
We will actually see the practical example in Python, and then it will be more clear to you. Okay?
okay,
As of now, you can just think of that we have gone through the theories, we have gone through Gini index, we have gone through information gain. Gini index tells you about the purity of the node. Gini index does what? Gini index tells you the thing, or about
okay,
the purity of the node, whether you can accept it as a conclusion or class or not. Okay. And information gain
what
tells
is,
you on which feature you should split.
okay,
Information gain tells you, with the help of Gini index only, it tells you on which feature you should try splitting. So with A feature you
okay,
are
but
getting
what,
some information gain, for B feature you are getting some information gain. You must go with that feature which has highest information gain. Okay?
okay,
Yeah, you want to say something? Ask something.
yeah, yeah, what this classification error will do?
Classification?
Third one, error, third one,
Okay, okay, okay. That is another measure, like entropy and Gini index only, which usually tells you, simply it tells the error in the splitting, like I will tell you example. Like here the classification error will be 0. Here the classification error will be something because the splitting is not good, and here also the classification error will be high because the splitting is not
Oh,
good. So it is same thing. I mean, if you ask me the formula, I mean I have not followed this classification error or something. Similarly, entropy is also there. It has again some formula and all the you know fundabaji basically behind that. So actually entropy were used earlier. Earlier, initially the entropy was only used, but these days, people are favoring Gini index, and they found it easy to implement and easy to, understand also, because it tells you about the
oh,
purity or impurity of the node. It tells you about the decisive nature of the split. So if you have say 100 images of cat and 100 images of dog, and suppose on some feature you are taking some decision, and that decision, suppose you had 200 images, say 100 of cat and 100 of dog, and suppose with some feature you splitted it like this: 100 dogs comes here and similarly 100 cats comes here. Now this is what I call the best split. If you will see the Gini index, it will be 0. Here also it will be 0. This is the best Gini split, where on splitting on that feature, it directly concludes the class, and that too with 100% accuracy.
okay,
Okay.
okay.
So yeah, so what was I telling? I was telling that yeah, we will see some example, Python example, when we will be implementing this decision tree. We will see that how this Gini index is calculated, and how you can also calculate the information gain in order to see which feature to take first. Okay.
Okay.
So more the information gain, more the chance of selection of that feature. So the feature which will have highest information gain will be the winner. Okay.
Yes.
Okay. So what we shall will do, I mean, shall we continue, or so we will see this in this decision tree. We will see through a Python example that how we can make a decision tree model on some iris data set, and yeah, we will see how this decision tree is made, and the split and all. Okay, so this is a typical example, a Python example, where I am taking iris dataset. Iris dataset we all know, right? That it has four
Mhm.
attributes: sepal length, sepal width, petal length, and petal width. And you have to tell the class whether it is setosa, versicolor, or virginica. Which is the class? What is the class of the flower? Okay, maybe we will take some other day. We will take some other example, some other data set also. For this decision tree one, maybe the initial first this model, we can take this iris data set. So see, in this program, what I have done, I have imported this data set, iris data set, that flower data set basically, where you have to classify setosa, virginia, and versicolor uh, flowers. So I am loading this iris data set from sklearn library only. Okay. And then if you remember, we had this stratified k crossfold split, where I will split the data set into 10, 9 part I will use for training, and last part I will use for testing, and then shuffle it 10 times. The testing data, the testing part will change every time, and the training will be 90% always. Good enough? So I am
Okay.
taking this stratified K cross fold with n splits equal to 10 again. Here I have imported it. Okay. Now with this stratified K cross fold, I am splitting my iris data and iris target. So why not we print this and see what is this iris data set? Because it's important initially to at least see. Okay, I
Yes.
will import sys, and maybe I will put sys dot exit. So it will run till here only. Now just see this is the iris data set. Uh,
Mhm.
why it is not printing? Okay, it is still loading maybe. So in, yeah, this is, it has come. You can see. See, this is the iris data set. It has 4 attributes, right? This one, this one, this one, this one. And see, the first few examples are of Setosa flower, 0 class, then few examples of first class, and then few examples of second class. So there are 3 flowers: Setosa,
Okay.
Virginica, and versicolor. And these are the labels basically. So
Mhm.
basically, if you see this row, or this row, last row, this is basically versicolor 2 class. So I mean, all this will be 2 class, and all this will be one first class, and all this will be maybe second class. I just wanted to show you the data set, that how the feature vector matrix is there, and the target is also there, the labels. Okay.
Okay.
Now if you see, uh, I will remove this. So now I am splitting this data and target, whatever data and target, into 90 into 10, 90 training and 10 testing. Okay. So I call this split function kf.split, and it will give me the 90% of the training index and 10% of the test index. It randomly chooses index. 90% of indexes it will choose for training, and 10% it will keep for testing. So I am creating two variables, xtrain and xtest. Xtrain is basically nothing but this from the iris.data. I am taking 90% of the indexes here, xtrain. And from text index, again, test index will be 10%, so xtest I am taking. Similarly, from target also, train index and test index I am keeping here. Basically, I have divided into my data into train and test, both the data as well as the target, the labels
Okay.
basically. Now here again, I am importing the decision tree, this tree somewhere from sklearn import tree. Now this tree dot decision tree classifier, when you do, you will get a classifier CLF, and CLF dot fit. X train, Y train. So
Training.
training data 90% you have given it for modeling the tree. Okay.
Okay.
And on the 10% of the data X test you are predicting through the classifier. Same. The basically the once you do this fit, your decision tree is learned.
Hmm.
And once your decision tree is learned, you can predict your testing data onto that. So I am predicting and I am getting this result. That result I can compare with this result Y test. Whatever target values were there for the 10% of the data. So here Y test and result I compare to in order to get the confusion matrix. And of course, so that confusion matrix and this goes on for 10 number of time. I told you in K cross fold validation. Once you get 92, then again the loop will carry on, and another 10% will be chosen for testing, and 90% for training, right?
Yes.
So that process continues till all the data is tested once, and confusion matrix I am keep on adding. So finally you will get something like this. The total confusion matrix you will get. I am also calculating that how many times the result matched with the Y test, the actual value, target values, and that also the track I am keeping. Once these things are done, you can print the accuracy and all. So just we will you know run this. Yeah, you see. You can see the result in the first iteration. 15 data points were 10% of that 150. Iris data set, how many samples are there?
No.
150 samples are there. In 150 samples,
50.
50
Okay.
setosa is there, 50 virginica is there, and 50 versicolor is there. Okay. So in 150, 10% of 150 will be 15, right? So 15 data
Yes.
point has been taken in each iteration for testing, and you can see the confusion matrix of them. I kept on adding all these small confusion matrix in order to get this bigger one. So the accuracy is 96%, and this is the confusion matrix for classifying setosa, versicolor, and virgin. With 95% accuracy, decision tree is able to tell. Okay. Now,
Okay.
this is a typical example how you can calculate and how you can train a decision tree and you can test it. What I will suggest, once I give you this file, maybe you can run it on your PC, and then you can just try printing everything. Try to print things and then see how this how Python works. So that is this. Yeah. Now the question which will come into your mind is, you will say that where is the decision tree? In the presentation you showed some decision tree structure and all. You talked about Gini index and information gain and all those stuff. So but where is that tree here? So what I have done in order to realize the decision tree, that how decision tree looks like, I have installed something called as pi.plus. Okay. I have installed this pi.plus, and if you see this particular line, if you read, it is for creating the decision tree in the PDF format. Okay. So
Okay.
whatever classifier you have trained here, na, CLF. So in the tree library only, which we have imported, there is a function called as export graphviz. This also you need to install. Graphviz software is there that you need to install. But what I am trying to say, the tree has this export graphviz where you just give the classifier and you give the feature names. Okay, whatever features are there, and it will, whatever this classifier is basically has learned a tree only, na? So that tree will be stored in this dot data, and this pi dot plus whatever we have installed, this pi dot plus will convert this dot data into graph. Pi dot plus
Okay.
dot graph from data dot data. And this graph you can write it in a PDF, irisvision3.pdf. Okay, and this PDF will be generated, which will tell you what is the tree. I mean, how does the tree looks like. So when we implemented this, right now we ran this and this accuracy has come. Uh, these lines also have been executed. So you see the parameter field equal to true, rounded true, special character true. All these things are just like that you can use. I will show you how the decision tree looks like. See, iris decision tree. This is the name of the PDF, na?
Yes.
This PDF has been generated here. Iris decision tree. Can you see this?
Yes.
See, this is the decision tree which has been learned. Now,
Okay.
you tell me how many samples are there initially. Sorry,
Uh,
sorry, I was wrong. I
55.
was wrong. Iris dataset does not have 155. Okay, no, 150, 150 only, 150 only. Yeah. See, initially, how
135.
many samples are there?
135.
Huh?
Training data. Training data.
Yeah. You see how many data
135.
points are there?
135.
135, which is 90% of
Yes.
150, right?
Yes.
So 135. Now, in 135, you have 45 what? Setosa, 45 versicolor and 45 versicolor and 45 virginica. Okay,
Okay.
this one. So if you calculate the Gini index, it will be like this. It will come out to be 0.667. If you will calculate this, na,
Mhm.
I don't want to calculate it, but I will just write the equations. The probability will be for all the class will be same, right?
Same. Yes.
And this will come out to be 0.667. Okay. Now,
Yes.
and you see the splitting how it is done on petal length. If the petal length is smaller than 2.6, go this side. Otherwise, go this side. And when you are going true side, you see this class Setosa.
Mm.
Amazingly, when you go on true side, 45 data points will be splitted on left side and 90 data points. See, so how many samples are came this side? 45. How many samples came this side? 90.
90.
And more interestingly, all these samples which came on left side are Setosa only. Rest are zeros.
Okay.
And here on the right side you see 90 points has come, 90 samples. Out of those, 45 is versicolor and 45 is virginica. So actually you
Okay.
cannot say that this is a good split. See, the Gini index is 0.5
Hmm.
because you are not sure of the split. Even after splitting, you are getting 45 of one class and 45 of another class. So you are not decisive. So the Gini index will be very bad. So if it is a pure node like this will become a leaf node. I mean, no further splitting will take place because already two classes are dead. But that's what I am telling. You go on splitting it until you come to leaf nodes like this, where you have, where you have a true split, Gini zero. You see, two sample came on this side, all both the two were Virginica. You see here 38 sample came this side, all the 38 were Virginica. Right?
Hmm.
So that's what I'm saying, like this you can make, and you can, that's what I'm telling you, you can calculate for each of the node, you can calculate the Gini and all, you will find the same. With the same formula, you can calculate the Guineas in this example also. But this is overall, I wanted to tell you that this is how a decision tree will look like. Okay?
Okay. Okay.
And on any of the non-leaf node, you can see there is some condition on which the split is happening. Sepal length, sorry, petal length, petal width, again petal width, sepal length. Some all the leaf node will have some condition. Now the
But what
question
is this?
here, yeah,
Yeah, 4.95, 4.85.
which
How
will,
this figure give this 4.95 and 4.85, this figure,
yeah,
how they arrive?
yes, that's what I am saying. The question here is, how do you decide that whether I should go for petal length, petal width, or sepal length or sepal width? How should I go about it? You have four options only: petal length, petal width, sepal length, sepal width. Now, which one to go with? So that's what I am telling. On each of the splits, suppose you are going to go with this split. You have come to this node and now you have to decide what is going to be my split. So on each split, just go with all the features once and calculate the information gain. How will you calculate the information gain? Information gain you can calculate with the Gini index of your parent and the child, right child and left child. Okay,
Okay.
and then you apply that formula of information gain. So you have say four features option. Okay, but you will choose only that feature which has the highest this Gini. So, I mean, first you will calculate the Gini and then information gain. So you will choose that feature like petal length here we have chosen, which will have the highest information gain. And if you will ask how come this information gain is calculated, so I will tell you that information gain is calculated by this this formula. Okay.
Okay.
So you have to calculate the Gini of root and then left and then right, and then you do it for all the features, and then whatever feature has maximum entropy, that is chosen for splitting in decision tree. Okay. But if you see the
Okay.
Python program, you don't have to worry about this splitting and all, because this two lines takes care of everything. These two lines takes care of everything.
Okay.
So this is how you can train a decision tree, and you can make a decision tree, visual decision tree like this. Okay. Now just few more things. When we have discussed so much about decision tree, few more things I would like to discuss. See, if you have a huge number of data points, if you have say 2000 data points, or 5000 data points, or 10,000 data points, and so sometimes decision tree is not a good idea to implement, because if you have huge data, which is always the case, decision tree sometimes overtrain itself. Overtrain means this decision tree will become very complex. Right now, how many levels are there? What is the depth of this tree?
Four
Five.
features.
Five, right?
Yes, five. Five.
1, 2, 3, 4, 5. Five. Now, if you have huge data, decision tree knows nothing. It knows only thing that it has to split. Okay. So if you have too much of data and it knows only that you have to split, and on non-leaf node, it should be pure node. All the all the leaf nodes will be a pure node, which will come to some conclusion or decisive measure. But yeah, so if huge amount of data is there, the random forest is there, but for sure you should not go with decision tree always, because sometimes this graph will even not be created, because it will be hugely complex model. You see here, only you see na, in this example only 6 samples are left, still you are doing the splitting. Now only 3 samples are left here, still you are doing the splitting. So sometimes it's good that even if the leaf nodes are not root, even if your leaf nodes, I mean, sometimes it's good that even if your leaf nodes are not, I mean, pure,
Hmm.
still you can just confine yourself there, right?
Yes.
So did you get this point? Say sometimes, see, the purpose is that all the leaf node will always be pure until the decision tree finds all the leaf node pure. It goes on splitting like that. But sometime, in order to prevent the complex decision tree, what people do, people will set the depth limit. They will say that you go on splitting if you wish to, but you cannot go more than 5 levels. So then the splitting will be done till 5 levels only, and the this you it may happen that on the fifth level your leaf nodes may not be pure,
Hmm.
but even that is good. See, that's my question. What is the purpose of these two nodes? Unnecessarily, these are making the complexity. Just for 3 data point, why I am splitting it again? So sometimes it's painful, because unnecessarily it will go on doing the splitting. Okay.
Okay.
So
Okay.
yeah, but at the same time, decision trees are very fast. You see, any feature you take, any I mean test example you take, it will always come to the conclusion just in 4 5 steps. Maximum worst condition I am telling you 4 5 steps.
Yes. Yes.
Okay, that is basically the depth of the tree. So it is very fast, but sometimes it gets overtrained, and for that, and that, in machine learning and decision tree terminology, it is called as pruning. It is called as pruning. Like you basically prune your uh, you know flowers, or trees, or whatever it is. Similarly, it is called as pruning. Like you are uh, cutting down your decision tree basically. So, otherwise, if you don't give anything, if you just run default, it will run everything. It will run until and unless each and every leaf node is pure.
Yes.
But
Yes.
got the point?
Yes.
So yeah, you do not worry about this, because we will be seeing again, on some other data set, we will see how decision tree works, and we will be seeing, but that we will see when we will do random forest. Okay,
Yes.
because random forest is another model, so which is based on decision tree only. So when we will be seeing random forest, then if first we will see what decision tree does, and then we will see what random forest, how random forest may improve the accuracy also. Okay, so that's all for decision tree.